Hello, everyone. I'm Jiaan from National University of Singapore. Welcome to my video submission for the AQIS 2020 virtual conference. In this video, I will introduce a recent piece of work by me and Dr. Khoon from Yale NUS College. In this work, we examine the behavior of the randomized benchmarking protocol in the presence of time-correlated dephasing noise. Randomized benchmarking, or RB in short, has emerged as a popular protocol to measure the overall noise level in a quantum processing system. For those unfamiliar with this topic, allow me to first summarize the steps specified in the randomized benchmarking protocol. It can essentially be broken down in the following steps. First, we construct the random gate sequence SM, which consists of m plus 1 gates, G0, G1 to Gn, each sampled randomly from a group of transformations G, under the constraint that they compose to the identity channel if these gates were noiseless. Here we use the tilde G to denote the actual implementation of the gate, while the untilde later denotes the idealized transformation of the gate. After preparing the random sequence, we feed it into an initial state psi 0 and measure the channel fidelity of SM with respect to psi 0. This figure would vary across different random sequences, so we may take many different random sequences of the same length and calculate their average in step 3. This produces one data point in the graph shown here. To get the full set of data, we repeat step 1 to 3 with different values of sequence length m. Finally, we fit the data for FFM as a function of m to a predetermined model. For the standard RB model, which is the most widely adopted version, the gates are sampled from the Clifford group and we fit the data to the exponential decay model, while A and B are unimportant fit parameters absorbing all the state variation and measurement errors. And the decay rate P is a key figure from a rate, characterizing in some sense the average noise level in the system. A schematic plot of this protocol is shown here, and the typical data set looks like this, where one fits the data to a straight line in a semi-log plot. You can find the application of randomized benchmarking in many recent literatures. Being easy to implement, it has been widely used to benchmark gate performance across platforms. You can find it in NV-centered qubit systems, semiconductor-based qubit systems, superconducting qubit systems, trapped ion systems, etc. Typically, one could indeed observe this exponential decay behavior of RB and is able to produce an estimation of the average fidelity through curve fitting. But curiously, some literature have reported data that seem awkward when fit to the exponential decay model. For example, in this paper by Forgatti et al., the authors provide a phenomenological explanation for this by proposing that the system has different instantaneous fidelities for each run. Some recent theoretical papers have also investigated this issue using an interesting viewpoint, whereby the fidelity decay is converted into a 3D random work problem in the Pauli space. Now, if we look at the potential culprit why this could happen, it's natural to examine the two assumptions used in the derivation of the standard RB protocol. One is weakly gate-dependent noise, another is weakly time-correlated noise. The issue of gate dependence is well addressed recently by few papers, and the conclusion is that even if we leave this assumption, we would still observe an exponential decay model. So the only potential reason for the non-exponential decay lies in the time correlation of the noise. In this work, we solve the problem of time-correlated noise by deriving the analytical expression for the sequence decay parameter on the time-correlated noise from the first principles, and illustrate clearly the contribution of noise correlation to the sequence decay behavior. To model the dynamics, we now make the following assumptions. The gates are abstract as instantaneous pulses applied periodically to the system, with unitary time evolution coupling system and the bus governed by some Hamiltonian. Note that we can always split the noisy G tilde into a pure transformation under the noise. So our assumption basically states that the noise arises purely from the unitary time evolution with a surrounding bus. Under this assumption, we can write the sequence channel as a following product of gates and unitary time evolutions. Focusing on the reduced dynamics of the system by discarding the information of the bus, we have a CPTP noise map for the system. To calculate the average sequence channel, we need to introduce a concept called group tooling. It is defined as a conjugate average of a channel with respect to a group. And this produces a block diagonal matrix corresponding to the irreducible subspaces of the group. Use the technique of splitting up random gates, we can write the average over different random sequences as a product of group-tooled maps. These maps are represented as diagonal matrices in a Pauli basis. Therefore, the matrix products can also be easily calculated. To make prediction on the sequence fidelity decay, we substitute this expression into the fidelity function by taking trace with respect to an initial state. At this step, we can already guess by observation that the sequence decay behavior would be non-exponential, as the average sequence channel cannot be written as some operator raised to the power of m. In our work, we also look beyond the standard RB protocol by considering alternative transformation groups. Specifically, we consider the Pauli group and the real Clifford group. These two groups are both transformation groups of the Clifford group. We label the Pauli, real Clifford, and the Clifford group by letter P, R, and C. The Pauli group is simply made of the four Pauli operators, I, X, Y, Z, where real Clifford group and Clifford group are defined as a normalizer of the Pauli group, restricted to the real and the complex field. These three groups satisfy the following relations as is demonstrated in the group structure diagram here. In terms of the number of elements, they grow from 4 to 8 to 24 in the single qubit case in the order of Pauli, real Clifford, and Clifford group. And in terms of the number of irreducible representations using Pauli basis, they goes from 4 to 3 to 2. Anyway, for the three different transformation groups, we have three different results for the average sequence channel. All are diagonal matrices, with Fm, Gm, and Hm on the diagonal entries. We call these functions of m as the decay parameter as it contributes directly to the fidelity decay of RB. We now introduce a unified notation for these groups by naming the decay parameters as P that takes the transformation group as an argument. These decay parameters can be experimentally extracted by preparing the corresponding initial state. We would expect the PM to recover the typical exponential decay law in the limit of no time correlation. Here I summarize the four solutions of the decay parameters under both the classical Gaussian noise model and the quantum spin boson model. In the classical noise model, the Hamiltonian is given by a sub-Hamiltonian of the qubit plus the time-fluctuating energy splitting. The BET function is modeled as a random Gaussian process with zero mean. With this Hamiltonian, we can write the decay parameters as a tuple average of an exponential function, where each entry of this tuple is taken from a base set A consisting of zeros and ones. The base set depends on the transformation group. For the quantum spin boson model, we start with a Hamiltonian of a spin and a bosonic field with linear coupling between them. Similar to the classical case, we can also write the decay parameter as a tuple average over an exponential function. But this time, each element of the tuple is a pair of numbers sampled from some group-dependent base set. But looking at the expression for P, there are also the gamma and phi functions in the exponent. This function plays key roles as they encode all the information about the noise. These functions are defined as the n-step decoherence function as generalized from the conventional decoherence functions. It is possible to define these functions in a unified equation where one integrates the dimensionless bass spectrum Sx with an oscillating window function, where the bass spectrum is the Fourier transformation of the autocorrelation function. The gamma and phi function correspond to the cosine and sine function, respectively. Apparently, this is an oscillatory integral, as you can expect by observing this example over here. As the level n increases, the integration kernel of the decoherence function becomes more and more oscillatory. This leads to a dramatic reduction in the magnitude of the decoherence function as n increases due to Riemann-Lebesgue lemma. So this leads to the key observation that as the bass spectrum Sx is smooth, we would have the following hierarchy of decoherence functions. Based on this observation, we can solve for approximate solutions for the decay parameter. For the zeroth order approximation, for example, we can neglect all other decoherence functions except the gamma 0. And this leads to the exponential decay behavior as found in the standard RB, which is expected as only time local noise is involved in the calculation. For the first order correction, we can truncate the sum in the exponent to include up to gamma 1 and phi 1 terms. This approximation takes account of the contributions from neighboring gates. In the end, we arrive at a 2 decay rate model, where Pm is characterized by 2 exponential decay rates, lambda plus and lambda minus. We can further calculate the decay rate shifts away from the zero order values of P1 and 0 due to the first order correction in terms of the decoherence functions. For classical noise, phi 1 equal to 0. This means that the shift for the lambda plus is always upward, while for quantum noise, both directions are possible. The lambda plus is close to 1 and lambda minus is close to 0. Therefore, in reality, the second term in the expression for Pm quickly vanishes and only the first term remains, leaving us the overall impression that Pm is an exponential decay. Now our approximation depends strongly on the validity of the truncation involving different orders of the decoherence function. To examine where the truncation would fail, we look at the extreme case of the DC noise limit, where the decoherence function, instead of converging to 0, is a constant. For this model, we can calculate the decay rate using the full expression and the zeroth order and first order expression correspondingly. Apparently, now the exponential decay model breaks as the data no longer fits a straight line, but we can see that by adding higher order corrections in our approximate formula, one gets closer to the full expression. The DC noise model corresponds to the noise with infinite correlation time. This is impractical in reality, so we examine the noise model with finite correlation time, specified by the cutoff psi, meaning the noise signals are uncorrelated as long as the time separation is larger than psi times the gate interval tau 0. We plot 3 different correlation lengths here. It can be proved that the gamma n becomes 0 for n larger than psi. But the first order effect, gamma 1, is always non-zero. Therefore, for finitely correlated noise, we can neglect contributions from the second order and above, as long as the correlation time is shorter than the gate interval. We further studied an example of a Gaussian-like spectrum. Its shape can be changed by varying its center and spread sigma. The decoherence functions for several different half-base sigma is shown in the figure here. As you can see, as the Gaussian peak gets flatter, the higher order decoherence function gets smaller and smaller. A reasonable approximation is that for sigma larger than half pi, we would have all the decoherence function approximate to 0 for n larger or greater than 2. This is somewhat expected as 1/2 pi is at least half of the period of the oscillatory trigonometry function for n larger or greater than 2. Therefore, the integrand would cancel out. This example here is important for more general noise, where there could be many other structures in the bass spectrum. In general, for the truncation to work, we need the bass spectrum to be relatively flat. Another observation is that since we define the dimensionless bass spectrum SS in terms of the gate time interval, the bass spectrum can always be flattened with shorter gate interval. In conclusion, it is directly demonstrated that the time correlation of the noise could contribute to the non-exponential behavior of the RB decay curve. We derived expressions for the fidelity decay, retrieving the expected exponential decay as the dominant term and offering expressions for the deviation from it as an expansion in the degree of time correlation of the noise. The validity of such expansion is analyzed in terms of the flatness of the bass spectrum and in terms of time scale set by the gate interval. For future studies, we could extend beyond the dephasing noise models used in this work to further explore the effect of time correlations on group symmetrization methods. That concludes my talk. For further questions, you are welcome to reach me at the following address. Thank you for watching.